Section 7.3 kind of outlines a couple of examples of how to employ the shell method, but I always think that it's always best to sort of have sort of a simple analogy that'll help make the integral make a little bit more sense, as we saw with the disk method last class. Um, with it's right there. As we saw with last class with the disk method, I think that the hardest part is setting up your graphs to figure out what is the area that you're supposed to be looking at and then revolving it around the axis. But once you actually set up the integral formula, integrating should be pretty straightforward. I mean, module one was all about integration techniques. So again, that should be the downhill part of these kinds of problems. Okay. But drawing a picture and remembering some of our algebra, that's going to be the tough part. So what I want you to do is like visualize a 3D cylinder made up of two circular faces, right? Very simple geometric formula. Let's go ahead and mute that. Okay. Um, the two circular faces have a radius r with a rectangular sheet or a shell wrapped around them, right? So this is the rectangular sheet. Sometimes you'll see um, kind of unfolded version um, of a cylinder drawn like this, where you have that rectangular sheet, and then there's two circles above it. Very phallic imagery right there, right? So, um, if you were to roll that sheet around, you would get that cylinder, right? Make these guys touch. All right. So we can think about the cylinder as having some sort of radius and some sort of height, and that can help us find like the surface area of that cylinder. Okay. So if we imagine now kind of making a hollow cylinder, so instead of a solid volume, just hollowing out that cylindrical shell, we can say that the thickness of that shell has some sort of measurement. We can call it W, right? There's some thickness there. And now that kind of changes the way we want to visualize what's going on with the shell and the hollow cylinder. And so the distance from the center of the circle, right, this inner circle here, to the inner edge of the shell can be represented by r, lowercase r, equals p minus w over 2, where p really just represents the distance from the center to the midpoint of the shell. So like from the center of the circle to the midpoint of that shell's thickness, right? This would be the distance p. Okay. So p minus this little distance here, w over 2, is just half of the width of the shell, or that thickness, will get you back to this inner radius. So we're using lowercase r to represent that inner radius, and p is really the kind of average radius to the center of that shell's thickness. Okay. So that's why you have to subtract half of the width of the shell. Okay. And then the distance from the center of the cylinder to the outer edge, represented here by capital R, is just going to be a very similar formula, which is equal to P, which is the distance to the midpoint, plus half of the width of the shell. Okay. So again, if we think about the distance from here to P, right, the midpoint of that shell, then we need half of that width to get to the outer radius. Okay. A little bit of a complicated, I think, uh, I don't know, a complicated looking description of this thing, but it's really going to help us understand how we get the volume of this shell. Okay, so the volume of the shell can be found by simply taking the volume of the solid cylinder and subtracting the volume of the hole. Okay, so this part right here, remember the P plus W over 2, that's basically the outer radius. capital R. And this P minus W over 2, that represents the inner radius, which I called lowercase r. Okay. And like I said, if you wanted to get the volume of this shell, then all we need to do is take the volume of the cylinder, which is pi times the radius squared, right? Times the height, and that would give us the outside cylinder. And then pi times the radius of the inner whole part of the cylinder squared times its height. And that kind of gives you like the hollowed out inner cylinder. And then you just subtract that inner cylinder to make a hole in that general shape. Does that kind of make sense? Okay. So with some algebra, this simplifies to a very seemingly very simple set of things that we're just going to multiply. So if you were to do a little bit of algebra here, you would get 2 pi times p times the height times the width. So we're just multiplying a bunch of things. Okay. But I think that is really useful to sort of step outside of this uh this like handout that I've given you all and actually do that algebra so that we can maybe brush up on our algebra skills and see what's going on there. So it should be like a pretty easy lift or like really easy to believe that we're just taking the volume of a cylinder and then subtracting the volume of the hole, right? But the algebra to make it turn into that like much simpler equation or formula is, I mean, kind of a lot. So let's think about this. We have pi times p plus w over 2 squared times h minus, I'm going to use a red color pen here to just rewrite this. So this is pi times p minus w over 2 squared times h. Okay. So if you look at these two terms, like this thing that's being multiplied and this thing being multiplied, what common factors do they have? They have a pi and they have an h in common, right? So like I'm just going to factor that out, pi and h. And whenever I factor, I like to use brackets, especially when I have all these complicated formulas. And what I'd be left with is this sort of this thing minus this thing, okay? So p plus w over 2 squared minus p minus w over 2 squared. Okay. But then squaring these is kind of a lot of work to do. You could do that scratch work somewhere else, but there's a really common formula. Like if you needed to multiply this by itself, you would do p times p, which would be p squared. Then you would do p times w over 2, and then w over 2 times p. So imagine that I'm foiling this out. So really, we're going to get two of these p times w over 2's. Okay. And then you would do w over 2 squared, which is going to be w squared over 4. Okay. So like that's what this guy would FOIL out into. Minus what the red guy sort of FOILs out into, and using a very similar formula, you would get p squared minus 2pw over 2 plus w over 4, and that's w squared over 4. Okay. And we still have all of this stuff wrapped up in these brackets, and the pi and the h are on the outside, sort of just hanging out until we're done with the simplification inside of the brackets. Okay. And I'm going to zoom in so we can see that a little clearer. Then we just need to distribute this negative sign here. So these guys in red are going to change signs. So we can write this all out again. Pi times h. And then in the brackets, we'll have p squared plus 2p times w over 2 plus w squared over 4. And then we're going to subtract p squared and then add 2pw over 2. And then we're going to subtract W squared over 4. Now you might think to yourself, why didn't I just simplify this term here, these terms here in the middle, right? The twos would cancel out. You could do that. Doesn't really make a whole lot of difference. I'm just trying to show you that, if you multiplied this, you would get P times W over 2, and then you would have two copies of that for each of those sort of multiplications that we did earlier. But regardless of how you decide to write that down, now if we look at all of the terms that are in the brackets, a lot of things cancel out. For instance, P squared minus P squared, that cancels. This 2PW over 2, that does not cancel because these are both positive. But with that, we would get 4PW over 2, which now, if you wanted to, you could simplify this to being just the 4 and the 2 cancel out. So this is 2PW. Okay. But then the W squared over 4 and the minus W squared over 4, those cancel out. So really the only thing we have left over in the brackets is this guy, 2PW. So that's pi times h times 2PW. And then for no good reason at all, mathematicians like to rearrange stuff and they like to put the constant in the front. They like to put pi next. They like to put the p next and then the height and then the width, right? So that's basically how we get this simplified formula. Maybe through a little bit of trickery of algebra, but the math checks out. Okay. So I didn't include this in the printout because I just wrote some algebra, right? This is not an algebra class, and I think sometimes when you're reading a textbook or if you're in WebAssign and you're reading the section that says like go to the textbook and read more, it would make this giant jump from this stuff to this stuff, and like you have to do the algebra yourself in order for it to make sense. Otherwise, you're just saying to yourself, I'm going to take it on faith that what the book is saying is correct, and I can just use that formula. So there's those two approaches, but like it's never going to make sense to you unless you actually sort of roll up your sleeves and do the algebra. Okay. But then if we look at this simplified formula, what this really is saying, if you recall, again, your basic geometry formulas, 2 pi r, if we're thinking about like just a circle, 2 pi r is the formula for just the circumference of the circle. So really, for these shells that we're going to be talking about, we have the circumference of the circle where P represents like the average radius, right? Because we had an inner and an outer radius, and if you go right in the middle, you get the average. Okay. So that's just the circumference of the circle, taking the average radius as the radius that we're using, times the height of the cylinder, and then times the thickness of the shell. Okay. All right. So let's see where we go from there. So basically, rewriting that in terms of the integral that we're about to prepare, we have two options for integrating. Sometimes we're integrating and revolving that solid around a horizontal axis, in which case, if that axis is horizontal, then we want to use the shell method with respect to functions of y. Okay, so then we would have 2 pi and then times the integral from c to d, where c and d are y values, times the function that we're calling the radius of the circle, times the function that we're calling the height of the circle, and then dy here is playing the role of the thickness of the shell. Okay. The vertical axis of revolution, depending on the problem, right, will be taking that integral with respect to the x values or the functions of x. So we would have 2 pi times the integral from a to b, where a and b are x values. P of x is now your radius, your average radius, but it's a function of x. H of x is going to be the height, but it's a function of x. And then d of x is playing the role of the thickness of the shell. Okay. A lot of sort of leading up to this. Does anybody have any questions before we go on to our first example? Or are you guys like eagerly waiting for the first example, right? The theory can be boring. I understand. However, like understanding the theory really helps you in a pinch when you get stuck on a certain problem to figure out like what is the radius that you're looking for and what is the height that you're looking for. Okay. So let's turn our attention to the first example. And if we need more paper, then we might have to write some more stuff down because I don't think I have enough room here. But the first example says find the volume of the solid formed by revolving this function, y equals x minus x to the third power, bounded by the x-axis, revolving it about the y-axis. So we got to draw a picture here. We need to know what this function looks like. And to me, this is going to be kind of a cubic function. Let me grab my calculator because I really don't want to do all of the heavy lifting like we did before. Let's try to make this a little bit easier on ourselves. But the picture is always going to be the most important thing. So I'm just going to type this function into my calculator. So y equals x minus x to the third power. And then take a look at what this looks like. And we want to revolve it around the y-axis. So I'm going to change this window setting or zoom back to standard, like so. Kind of a bad looking graph, right? We want to see just this part that's bounded by the x-axis. So let's zoom in a bit. Let's see if this is too much of a zoom. Okay. Well, let's go ahead and draw this picture. So I'm going to draw this here, x and y axis, and then my function. You can call this f of x if you wanted to, x minus x to the third. It, from looking at the graph, it kind of looks like it passes through the origin and then passes through, I want to say 1, but I don't know that for certain. Okay, there are ways to do this in the calculator where you can find those endpoints, but I like to go ahead and review the algebra. So I want to see where this thing is passing through the x-axis, and the x-axis has a y value of 0. So I'm going to set this equal to 0, x minus x to the third power. And this is how we find, for instance, the, what do we call them? X-intercepts. To find the x-intercepts, you can set that function equal to 0 and then solve it. And this should be a nice, easy factoring. So this is going to be x in common, and then we have 1 minus x squared. And so if we set these two factors equal to 0, we can go ahead and say that one of our solutions is x equals 0. And then this guy would be 1 minus x squared equals 0. We can move the x squared over to the other side. So 1 is equal to x squared, positive now. And then take the square root of both sides so that we get plus or minus 1 is equal to x. So kind of 3 x-intercepts there, but we can kind of see that on the graph, right? The graph is intersecting here at -1, at 0, and then at 1. Okay, so over here is our x value of 1, and our graph kind of looks something like this. And we want to revolve this around the y-axis, like so. Okay. Okay. So let's think about how that shell is going to look as we're drawing this picture. So what the shell is going to look if we're revolving it around the y-axis is kind of like, and here's just like an example of the shape. If we revolve, let's say we make like a characteristic little rectangle here, and then revolve that around the y-axis. This is -1 over here. Then you could sort of imagine, I'm going to draw the other part of the shape here, which is like so. another little characteristic rectangle here. And the shell kind of wraps around like so. Okay, kind of a cylindrical drawing there. Okay. On the graph space, that's kind of hard to sort of visualize. So you have to think of it like, okay, we have a cylinder that looks something like this once we're done revolving it, right? This kind of, to me, looks like a vertebrae. Okay. And the characteristic, this representative rectangle just is helping us understand like the different parts of the function, right? And how we find the volume of the cylinder. So the radius of this is going to extend from kind of like the center or the y-axis to the center of our rectangle, like so. And then the height, I'm going to put P there for the radius. Okay. And then the height of the function, or the height of the shell here, looks like it's determined by the height of the function, right? So the height here is just the function that we have ourselves, f of x. Okay. Okay. But what does p represent? Because remember that p is supposed to be a function of x. And you kind of have to think about like as we are integrating, let's say from 0 to 1, right? That if we were to draw like another rectangle sort of somewhere more close to the y-axis here, you would get like a tinier shell that was like embedded inside this larger shell that we drew. So you could think of it like we're putting a smaller shell inside of here, and then kind of doing this Russian nesting doll thing where we're getting smaller and smaller shells inside of each other until we take up the entire volume that's represented by the shape of this function. Okay, so kind of like Russian nesting dolls, or like those layered cakes where you have like a larger layer at the base, a smaller layer. There's just smaller smaller cylinders stacked on top of larger ones. Okay, so that means that if I were to draw like another rectangle, like right here, well, then the radius there would be just some other x value here, right? So if the radius is just determined by whichever x value that we're at, then the function that represents the radius is just going to be x. Okay. Okay. That's going to take some practice, but now we can think about our geometric formula, right? We have this 2 pi, was it PHW, and we're going to sort of um, think about transforming this into our integral for volume. So the volume is going to be 2 pi times the integral from 0 to 1. And since we're revolving it around the y-axis, we definitely don't want to go from negative 1 to 1. We want to go from 0 to 1 because that revolution, the multiplying it by 2 pi, is what's going to take us around to the other side. So we'll pick up this volume over here. But then we said that the function p, which is the average radius, is just x. The function of the height was just the original function we were given, which is the x minus x to the third. And then the thickness or the width of the cylindrical shells is just going to be dx. Okay. So the setup is the hard part. Drawing the pictures and imagining this in 3D space is the hard part, but now we can take this over to another sheet of paper where we can actually do the work. Before we start integrating, does anybody have any questions or comments about kind of how to draw these pictures? Obviously, this is the first example. I know it feels maybe overwhelming, but any thoughts, comments that are popping out at you? Okay. So yeah, I didn't give myself enough space on this page. So we're going to do another page. So we're going to go ahead and say the volume is equal to 2 pi, going from 0 to 1, x times x minus x to the third dx. And with some algebra just to help us simplify some stuff, this integral, we can go ahead and just distribute the x here. So x times x is going to give us x squared. X times x to the third is going to be minus x to the fourth. And then we have our dx here. So now we have 2 pi, and we can go ahead and integrate this. So this should be 1/3 x to the third minus 1/4 x to the, sorry, I messed that one up, right? X is 1/5 x to the fifth. This is why I tend to do the exponent part of the integral first, so that I remember what the denominator should be, right? So that goes up by 1, and so the denominator should be 5. So, and then that's the integral, right? Pretty straightforward integration of a polynomial, and then we just need to evaluate that from 0 to 1. So we can say this is 2 pi, and then 1/3 times 1 to the third minus 1/5 times 1 to the fifth. Subtract 2 pi, 1/3 times 0 to the third minus 1/5 0 to the fifth. And the nice thing here is that this thing that we're subtracting happens to be 0, so we can go ahead and cancel this entire thing out and just focus on this guy. So we're just really looking at 2 pi times 1/3 minus 1/5. And we'll just throw that in the calculator. I'll leave the 2 pi by itself. I'm just going to do the fraction part first. 1/3 minus 1/5 is 2/15. So this should be 4/15 pi. And that's the volume using the shell method. Questions, comments? Did I lose anybody anywhere? Okay. So we really just need to practice figuring out what the image is going to look like every time. I think that's it's going to be like 70% of all of these problems is just making sure that you select the correct function for the radius and the correct function for the height. Okay. So I'll put that there. Okay. Put that there now. All right, we'll do our second example now. Find the volume of the solid by revolving the region bounded by the graph x equals e to the negative y squared power and the y-axis about the x-axis. Okay, so I'll make a little note here. Actually, I want a little bit more cushion underneath this. The note is that we've been given this thing, which is a function of y. Okay. So let's figure out what this thing is going to look like. Um, and then we can go from there, right? Because that's really the way we have to do this every single time. So if we have x is equal to that, what could we do? Hopefully my graph isn't too small. Okay. Um, have no idea what this looks like in terms of x, but let's go ahead and say maybe we can find the y-intercepts or the x-intercepts. We can try that next. But the y-intercept is always just plugging in 0 for x and then solving it. That might be a hard equation to solve, but I'm just taking a guess at, how can we find some of these critical points, these really like important features of the graph. So if I did x is equal to e to the negative 0 squared, then that's just going to be e to the 0 power. So x would equal 1. Okay. And I totally messed that up. Let me get this is not what I did. So I said I was going to set x equal to 0, but what I did was I set y equal to 0 because it's an early morning for all of us, right? So if I set y equal to 0, then what I just found was the x-intercept. Okay. And this is why we use pencil. Okay, always good to find those mistakes though before it causes any kind of mayhem. So x equals 1, y equals 0, that's going to be over here. Now we can find our y-intercept like I intended to before, and for the y-intercept, x is equal to 0, so that was true, but I just plugged it into the wrong place, so that would be 0 is equal to e to the negative uh, y squared. But this kind of looks hideous, right? And maybe if I tried to kind of cancel out this e here, if you recall your basic algebra, usually you would take the natural log of both sides of the equation. But if I took the natural log of 0, then I'm getting an error, right? Because the domain of natural logs has to be a positive number. It cannot be 0. So this isn't going to work. Okay. So this we can say is undefined. So that didn't really help us. So let's maybe think about this a different way. If we graph this, now I know that this says y 1, but I'm going to put this as just kind of swap the variables, right? Y equals e, where's e? E raised to the negative x squared power, and then graph it. Now, usually what you would get when you graph this in terms of x, you kind of have to rotate it this way in order to see what it looks like in terms of y. Okay. That might be like a little trick that maybe you're not like super familiar with, but the alternative is going to Desmos and just graphing this in terms of y, which I think is always a really good option. So we could say this was x equals e raised to the negative y squared power. And then let me go ahead and share this graph with you guys. Right? Isn't that exactly like what we did when we graphed it and just rotated the calculator the other direction, right? Just 90-degree rotation. Okay. So it's no wonder that we didn't have a y-intercept because like this function looks like kind of a I don't know if you guys are familiar with statistics, but it kind of looks like a normal distribution, like a bell-shaped curve. And technically, right here at the y-axis, there's an asymptote. The graph is not getting going to touch or cross there. It's just getting really, really close to the y-axis, but will never touch or cross. That's why we're um, never going to get a y-intercept. Okay, so let's zoom back to our drawing that we're making. Okay, so I just drew the upper half of this function, but now we said that we wanted to rotate this about the x-axis. So let's go ahead and sort of set up these shells the way we want to. So we're rotating about the x-axis, which means that these shells, the representative rectangle is going to be something like this. Here is my rectangle. If we're rotating about the x-axis, then we're going to kind of be rotating into what we usually would consider this negative space. So think about this bell-shaped curve continuing on down here. And now when we rotate this, we should have kind of an image symmetrical going up here to have another rectangle. And we're just building that shell. So we would have something that looks like this. And then you can also connect these like so. Okay. So think of it like a cylinder that's laying on its side. Okay. So you can either use the graph here. I think if we start writing more stuff on the graph, it gets confusing, but we need to think about what is the radius here, P. And then if this is kind of like a cylinder laying on its side, then this part here, the height is going to be in terms of y, right? Right? Because our function's in terms of y. So like the radius, if you think about it, is extending from the x-axis to sort of the center of our rectangle, right? So that means that P of, let's put it over here, P of y looks to me like it's just going to be determined by, actually, it's going to be determined by wherever we are on the function, right? That's going to be the same thing. So wherever we are on the function, that's determining the radius. So if that's the case, then e to the negative y squared is going to be our radius. And then the height of the cylinder is just this distance here from here to here, h of x. Okay. Oh no, I have this wrong. Um, the height is going to the edge of the function, right? Yeah, that's the way I was thinking about it before. The height is actually the edge of the function. So h of x is equal to the e to the minus y squared. And then if that's going to the edge of the function, then the radius is going to be whatever y value we happen to be at. Okay. Yeah, that makes sense to me. Because if I were to draw like another larger shell around this guy, then the height would be I'm sorry, the radius would be whatever that y value is. Yeah. P of y. So that's not this. P of y is just the y value. Okay. So again, it takes a little bit of trickery to figure that out. But if we think back to our little analogy, 2 pi times that average radius times the height times the width, that's going to help us set up our integral. So the volume should be equal to 2 pi. And then we're integrating from the some y value to another y value. Okay. And um, let's just go from 0 to 1. Okay. In this case, the text example I forgot to write said that the y value we're looking at are just going to be from 0 to 1. So they're giving us straight up what our limits of integrations are. And then it's p, which we said is just y, times the function, which is e to the negative y squared, dy. Okay, now let's go ahead and take this integral. V is equal to 2 pi, integrating from 0 to 1. And then we said it was y times e to the negative y squared dy, right? So what integration method do you think we have to use here? Just to get some, yeah, u substitution. So what are you thinking the u is going to be? Yeah, I'm thinking that this is going to be our u. So like if we set that to the side, u is equal to negative y squared, and then we take that derivative, we should get what? Negative 2y dy. Okay. So that means that if I have a y in my function and a dy, then I should be pretty good to make that substitution. But we're going to go ahead and sort of move this negative 2 over to the other side of this equation. So we have negative 1/2 du is equal to y dy. So just making that substitution here, 0 to 1. The y dy, we can go ahead and replace that with negative 1/2 du. So that's just going to be now e to the u times negative 1/2 du. And the 1/2 is going to cancel out the 2. So this is going to be a negative pi out here, 0 to 1 eu du. And then what is the integral of e to the u? Well, that should just be e to the u. But remember, we need to go back into our original variable. So this is going to be negative pi e to the negative y squared. And then we're going from 0 to 1 to evaluate this. So this should be negative pi times e to the negative 1 squared minus negative pi e to the negative 0 squared. Okay, so let's figure out what this is. So that's going to be negative pi e to the, it's just going to be negative 1 up here, minus, well, really, it's going to be a plus now, pi e to the 0. Okay. So if we wanted to, we could factor out the pi. I think that that makes a lot of sense here. I'm going to factor out the pi. I'm just going to rearrange this so that I put the positive thing first. E to the 0 is just 1. Okay. And then I'm going to subtract. This would be 1 over e. So again, I'm just going to kind of draw little arrows to show you that I rearranged this problem. But that's actually the answer. 1 minus 1 over e. Kind of an ugly looking number, but if we wanted to go ahead and check to see, our volume should be positive, we can go ahead and throw that into the calculator to see what it ends up being. So like pi times 1 minus 1 over e, and we get 1.958. Okay, so I'm just going to round that to 3 decimal places just for good measure, 1.9. Sorry, I had a little dyslexia there, right? I think I said 598 or something like that. 98, and I'm going to round this to 6. Okay, so rounded to 3 decimal places.
When did the pi change to
When did what pi change to positive? Which pi?
the
The second one?
no the first one?
This pi here?
Yeah.
It didn't change to positive.
You just moved it.
What I did was
What
I
else did you do?
factored out a pi and I left the negative, yeah, and then this stayed as that negative 1 over e,
Yeah.
and I just put that positive thing in front, right? Yeah, and that's always the trick. Like that's the hard part whenever your instructor or whenever the textbook starts to do that thing where they just like kind of skip steps and then they rearrange it and you're like, okay, well they just made 3 moves, but they only changed 2 lines. Okay, so you do have to be aware of that. And what I would say is like whenever you're not sure what they did, you bust out another piece of paper and then just like try to see if you can fill in the gaps. Okay, because if you can make your algebra sort of rearrange and then get what they got, then you're on the right track. And also you're honing your algebra skills a little bit there. Okay, so maybe I'll say here that I factored out the pi. Pi. Okay. Any other question? That was a good question. Then we're on to the next example, which I haven't written down yet. So that'll give you guys some time to write this down. So this one says, find the volume of the solid formed by revolving the region bounded by the graph of y equals x squared plus 1, y equals 0, x equals 0, and x equals 1. And we're revolving about the y-axis. And I'll pause for anybody who's... Okay. Again, we need to draw what this thing looks like. luckily, they switched us back to a function in terms of x. So I always find that for me personally, a function in terms of x is kind of easier to look at, but then there are some times where you have to decide for yourself whether it's going to be easier to use the disk method or the shell method because both can be used sometimes to find that volume. Okay. So I think that becomes a little bit tricky to figure out which one is preferable. So again, before we get into that, let's just draw this picture to see what we're looking at. So here's my x-axis, here's my y-axis. Okay. And they said that we're looking to be bounded between y equals 0, which is going to be the x-axis itself. X-axis is y equals 0. And then x equals 0, which is the y-axis. And then x equals 1, so out here somewhere. Okay. Now, what does this function look like on the endpoints, we might ask. So if we take our function, I'm going to call it f of x is equal to x squared plus 1, then what we could do is set the x value to 0 to find the y-intercept. And that is just going to be f of 0 is equal to 0 squared plus 1, which is just 1, right? So that means that our x value is 0, our y value is 0. I'm sorry, 1. So we're going to be up here, and that will be our first point of interest. Then if we wanted to find this x-intercept, the x-intercept is where we set the function equal to 0, or sometimes we say the y value equal to 0. So that would be 0 is equal to x squared plus 1. But if we did that, then I'm already seeing some trouble, right? Because we would have to subtract the 1 over to the other side. And then once we take the square root of both sides, x is equal to plus or minus an imaginary unit. Okay, so that means that we're not going to have no x-intercepts. So when all that fails, then we can go ahead and say, well, let's just graph this thing to see what this image looks like. Okay, so I'm just going to go ahead and say we have our graph of x squared plus 1. That makes sense to me because this is a parabola that's just been shifted up by 1 unit. So my drawing of this graph is too close to this sort of stuff that I've drawn here, right? But it looks something like this. Okay. So if I wanted to find like this point over here, then all I need to do is plug 1 into my function to find where that point is. So that might be another point of interest, just one of the endpoints. So we'll go back over here and do some other scratch work. So f of 1 is just 1 squared plus 1. That's just going to be equal to 2. So this has a y value of 2. So that's 1 comma 2. Okay. Now, this drawing is not great. I went way too close to the text here that I was trying to get. So let me draw a much nicer image of this, so I have some more room to breathe. Now that we kind of have our endpoints kind of situated. I know that this is 1, and I know that this is 2, and this is 1, and the graph looks something like that. And we're rotating around the y-axis, right? So we're rotating around here about the y-axis. And so we need to think about the shell method, but the problem here is that basically the function doesn't exist, or doesn't like kind of the function is not really involved in creating a shell that's below one on the y-axis, right? So like you can think of dividing this into two parts here, where you have like this upper part. If we needed to, we could come up with what those shells would look like. And if we drew kind of a rectangle here, let's see. Yeah. Let's say if I drew a rectangle here with respect to, how do we want to do this? Like, there's a couple of different ways that we could find the radius. Let's just draw a rectangle here. Um, right there. Right? What would the shell look like if I did something like this? Well, the width of the shell looks like it would be delta y because you're going in the vertical direction, right? So that would be like if we were integrating with respect to y. And then like the radius, since we're rotating around the y-axis, would be like this distance here. So that radius p. Um, but then down here, this rectangle has nothing to do with the function, right? Because the function is right here. This is y equals x squared plus 1. So this is a delta y. And also, this shape down here doesn't seem like it has a hole cut out of it. Like there's no inner radius, right? This just extends all the way to the y-axis. So you could think of this like lower portion as being kind of a solid cylinder. And then this one up here would be like a hollowed out cylinder. So, like, is this the way that we want to integrate it? Well, if I draw that picture again, and we think about like imagining the cylinder a little bit differently, same image, just a little bit different, right? Why couldn't we, think about a representative rectangle as being from here to here, and then rotating it around the y-axis so that our cylinder makes a little bit more sense? It's in the upright position. And so if I were to go ahead and draw sort of like the mirror image across the y-axis, which is exactly where we're trying to rotate this thing, it would look something like this. And we'd have another rectangle over here, the edge of our cylinder. And so we would have this kind of drawing here. So this one looks like the better setup. Also, your rectangle is kind of like its width, its thickness is going in the left to right orientation. So it's like that's going to be delta x. And since our function's in terms of x, that makes more sense. Then we also know that from the center of our cylinder to the center of our little representative rectangle, whatever that is going to be p of x, which that radius would extend to the edge of our function, right? Or actually that radius just extends to whatever x value we happen to be at. So that's going to be just x. Okay. And then the height of the cylinder here, that height is going to be equal to, going from the x-axis up to our function. So the h here is going to be equal to the function, which is x squared plus 1. So like to me, this cylinder makes a lot more sense, and we can sort of like layer those shells inside of each other as we're sort of integrating from 0 to 1. Okay, and remember the 2 pi part of the integral takes care of the rotation around the y-axis. Okay, so we want to have these like cylinders kind of stacked up, but like this is the thing that's going to get complicated. What we need to do is like every time you need to draw maybe a couple of the drawings and see like what is going to be the most ideal or the clearest version of this shell to you. And so the shell method can be a little bit more complicated to employ because of that reason. We didn't want to do these shells. Also, like usually when we rotate these shells, we rotate kind of in the perpendicular direction. We rotate perpendicular, but like the axis of rotation would be parallel, but we're not rotating around the x-axis, right? So this drawing that we were doing here didn't make any sense, right? We wanted to rotate around the y-axis, and so setting up that rectangle sort of parallel with your axis of rotation is going to help us set up those shells. So I'm going to put a little note here. Note, you want to set up the shell or the rectangle parallel with the axis of rotation or the axis of revolution. But then we'll bring in our integral formula if we have this set up. And that's just going to be 2 pi. Remember, that's the thing that's going to rotate us around the y-axis. We're just going from 0 to 1 in terms of our limits of integration on the x-axis. We said that the radius here is just going to be, the radius of each of the shells is just going to be whatever x value we happen to land on. So like if I had a radius of a shell that was going a little bit further out, the radius is just landing on an arbitrary x value, right? And if I had a radius that was a little bit closer, then it would just be some arbitrary x value, and that's why the radius is just x. And then the height is going to be wherever we're stopping on the function itself. So times the height, which is x squared plus 1. And then the thickness is the delta x, but as an integral, we write that as dx. So this is not the ideal image up here. We kind of want to ignore that as much as we can. Yeah. Okay. So let's go ahead and take this integral because it looks pretty straightforward, right? If we wanted to simplify this a little bit more before we begin, it's going to be x to the third power plus x and then dx, right? So that's going to be 2 pi 0 to 1. We said x to the third power plus x dx. So we should get 2 pi. And then when we integrate, this should be 1/4 x to the fourth plus 1/2 x to the second power, integrating from 0 to 1. And so we should get 2 pi. 1/4 times 1 to the fourth power plus 1/2 times 1 to the second power minus 2 pi 1/4 0 to the fourth power plus 1/2 0 to the second power. And then luckily, what happens to this part of the integral over here? It's just 0. Yeah. So that's gone since it's just 0. And then we can just go ahead and simplify this a little bit more. So this will be 1/4 plus 1/2. This is easy. in my spare time, I do a lot of baking. I make some pizzas and make some banana breads from time to time. So like if you have a fourth cup and a half cup, you should have 3/4 cup, right? So that's 2 pi times 3/4. And then that simplifies to 3 pi over 2. Okay. Now, we could integrate that a different way, right? Let me sort of go back to this idea here, right? Let me zoom out. For this um, first image that we did, I was trying to do the shell method, but like when you set up the shell method, these rectangles are usually going to be parallel with the axis of revolution, right? So like if I set up this rectangle, then it kind of looks like I'm gearing up to rotate it around the x-axis, and that's not what we wanted to do. However, if we had thought about this as could we have applied the disk method, writing this function in terms of y, then we could have rotated a disk around um, around the y-axis in this direction. So I want to show you guys that you can use the disk or the washer method to find this same integral, but it is a little bit trickier. Okay, so let's do this one again, but now using the washer method. So kind of like going off script here, just to make sure that we can interchange the two methods, but also integrate with respect to y. Okay, so this is going to be off script. We want to find the volume of the solid, uh, revolving the region bounded by y equals x squared plus 1, y equals 0, x equals 0, and x equals 1 around the y-axis using the disk slash washer method. And let's see if we can sort of make sense of this. So going to just draw the exact same graph here. I'm not going to take the time to find the endpoints and all that jazz because we already did it, right? We did the heavy lifting. This went to 1. That high point went to 2. And then this went to 1 over here. So we had a graph that looked like this. Okay. And do you guys happen to remember the formula for the disk method? Disk slash washer. I think it was 2 pi r. Was it 2 pi? It was pi because it was the area. And then you integrate, and then you found the outer radius, right, minus the inner radius. So I'm going to put it like this. Outer radius squared minus the inner radius squared. These guys were in little boxes here too. All of that dx, right? If it was a function in terms of x, right? If it was a function in terms of y, then it was pi, and then same deal, r in terms of y squared minus r in terms of y squared, and then that whole thing dy. Okay. So again, we want to revolve this around the y-axis. So we have to think about like for our limits of integration, if you think about breaking up this shape into two distinct regions, we have this region here that goes from 0 to 1 on the y-axis. So for that region, we just need to think about, okay, well, what is the shape of the disk that we're making? And that disk doesn't have like, it's not being hollowed out by the function. So you can think about this lower region, which goes from a y value starting at 0 and then going to 1 as being just a solid cylinder, right? So all we need to do there is get really pi r squared to get the volume of that cylinder, right? And then multiply it by the height or the thickness of the cylinder, if you want to think of it that way. Okay. So what we would have to do though is get this function in terms of y. But even then we don't really need that because what's the radius here? What is this radius from the axis of rotation to this x value of 1? Anybody know the distance from 0 to 1? It's just 1, right? So the radius is just 1 in this case. So the radius is 1. Okay. And then the height, well, what's the height here? From 0 to 1? The height is 1, right? So for this, we don't even really have to integrate it. We can just say that that's going to be um, pi times 1 squared times 1, which is just pi. So this lower area, or that lower volume, has a volume of pi. And then we just need to add that to the um, the volume that we find of this upper region here once we rotate it around. Right? And kind of get this bowl shape. Okay. So if you think about the radius here, the radius of the internal function, the one that we're sort of carving out, the lowercase r for these functions, that's going to be whatever the function is, right? In terms of y, though. So let's go here with the upper region. And that's going to be integrating from 1 to 2. So that's going to be from 1 to 2. The inner circle, or the inner, the whole, has a radius that's equal to our function, but in terms of y. So f of y, which means that we have to rearrange our function to get it in terms of y and not in terms of x. So that would be like saying y is equal to x squared plus 1, and then rearranging it so that you get x squared is equal to y minus 1, and then x is equal to plus or minus the square root of y minus 1. But we really just want the positive part there. Okay. So r of y is going to be equal to this square root of y minus 1. That's going to be the inner radius, right, for the inner circle here. Then for the outer radius, it looks like it's just outer radius, or the outer circle, capital R of y. I mean, it looks like that's just going to be a radius of 1, right? So from 0 to 1, right? So that's just equal to 1, right? That's what that distance is. That distance is not going to change. And so once we figure out what our inner radius is and our outer radius, we can go ahead and plug it into this function here to figure out what the volume should be. Once we find the volume of the upper region, we can add that volume to the lower region, which we already found here. Okay, so I'm going to go ahead and do that, and this is being recorded for posterity. So if this isn't making any sense, if I'm dragging you guys through it, then hopefully you can make sense of it later. The volume of the upper region is equal to pi on the outside, and then it should be the outer function, which is just 1 squared, right? Outer function squared minus the inner function squared. And the inner function we found to be the square root of y minus 1 squared. All of that dy. So that we have now pi. And we're just integrating for the upper region from 1 to 2. Integral from 1 to 2 of 1 minus the square root cancels out this square, so we should just have y minus 1 here, dy. Then with some little algebra, we can say that this is going to be 1 minus y plus 1 dy. And the ones here are like terms, so we can go ahead and rewrite this yet again to 2 minus y dy, and then that's a really nice integral. So we have pi 1 to 2. This will be, actually we're integrating now, so don't need this guy. We will just have 2y minus 1/2 y squared, and evaluating that from 1 to 2, pi times 2 times 2 minus 1/2 times 2 squared minus pi times 2 times 1 minus 1/2 times 1 squared. And let's go ahead and simplify this a little bit further. Let's factor out the pi's, make that a little bit easier on us. Okay, this is going to become 4. That's going to be 4 times 1/2, so that's 4 minus 2. We factored out the pi, so this is going to be a minus 2 here, because I'm distributing that negative sign. Minus 2. And then this is going to be a plus 1/2. Hopefully my mental algebra there didn't fail me, but we're going to get something here. 4 minus 2 minus 2. Those are all going to cancel, right? Because 4 minus 4 is 0. So this is going to be pi over 2, right? and that's the volume for the upper region. And if I add that to find the total volume, we found pi before plus pi over 2. So that should give us 3 pi over 2. Okay. And that's exactly the same thing that we found when we integrate it with the shell method, right? And that's a great place to call it. And just to summarize, like, if you guys felt like that last example was like way too complicated, you're going to start getting some problems in the homework that say, just find the volume of this solid. So you have to draw that function out and like create the diagram for yourself and then determine, is this going to be easier to do with the disk method or the washer method, or is it going to be easier to do with the shell method? Because usually one of those methods will make it easier to find that volume. You can most of the time use either method, but like we saw with this one, if we use the disk or the washer method here, we had to break it up into two regions and then find those volumes separately and then do a lot of algebra trickery to sort of put it all back together. When we did this with the shell method, we just had one simple integral to take care of, and there wasn't that much work on our part, right? So just make sure that you're getting into the homework and that you're practicing some of these things. Do not delay on that because as soon as you realize that you need help, that's usually when help is not easy to find. So just make sure that, my recommendation is always to go to Math World, do your homework in Math World, Zoom with the tutors. They'll leave you alone if you don't have any questions. But if you're using the Math World Zoom and you're just doing your homework while logged on to there, if you have a question, you can just hit that button that says ask for help and somebody will pop in and sort of either jump into the trenches with you and try to help you dig your way out, or they'll be your savior and they'll say, okay, this is the thing that we're missing and this is how we need to find our integral. Okay. So that's all I have for today. I will see you guys next week. If you have any questions, just shoot me a message in Canvas if you need me. Otherwise, I'll see you guys later. Have a good weekend.